Hello, my chemistry faithful. Video 2. Let's get into the vocab of the nuclear unit. Do we know what these words mean? First one is an old word that we learned back in atoms, and this is isotopes. We will get into isotopes in a little bit more detail for this unit. This is same number of protons, different number of neutrons, hence same atomic number, different atomic mass. So this unit will serve as a great review of atoms and get us back into reviewing atoms. So one of two or more atoms with the same number of protons but a different mass. That is technically an isotope. And then a radioisotope is just any isotope that's made radioactively. So this is naturally or artificially produced radioactive isotopes of an element. We will be concerned with those very much in this unit. So we can call them radioisotopes. Radioactivity. This is all about any of the transmutations that could happen. And here is alpha, beta, gamma, I see. This is the emission of radiation or particles caused by the spontaneous disintegration of atomic nuclei. Basically, when the nucleus gets too big, it becomes unstable. Hence, we talk about nuclear stability. Okay. Nucleus is stable, meaning that it does not spontaneously emit any kind of radioactivity or radiation. This is nuclear stability. The nucleuses of atoms want to become stable. Okay, and if they are unstable, then they will transmutate into something that is stable. A nuclide is the result. So this is the atomic species characterized by the contents of its nucleus, its number of protons and neutrons. So it's just basically looking at the nucleus of an atom. Conservation of mass, just like when we were doing balancing equations, we have to conserve mass here too. So protons and neutrons, they'll have to be accounted for somewhere. And knowing that, I can solve like where that question mark is. So when we have to solve these equations, it's going to be this simple. You'll see that 92 on the left is 2 plus 90 on the right. That's 92. And 234 plus 4 is 238. So it's literally, the math is going to be that simple. Gets a little funny when you see the -1 because now I know it needs to be a 91 because 91 plus a -1 is 90. That's the only time it'll get a little tricky. Total atomic mass of reactants equals the total atomic mass of products. Both the mass and the atomic numbers have to add up. Okay, natural transmutation. So this is a natural decay, right? When an element turns into a different element naturally, only one reactant. That's the trick for us. So when you see it in a transmutation equation, if there's just an element turning into some of the other things, that's natural. There's only one reactant. Artificial, see how there's a neutron in this picture? So if I hit a neutron, I get that neutron going really fast and I hit that uranium, I can break that uranium. That's called fission. So this is when an element turns into different elements with the help of another particle. Hence, there must be two reactants. And it's also kind of slang for man-made artificial transmutation. Okay, fission. Fission is the cutting. So here I'm going to hit that same 235 uranium with a neutron, and it's going to break it apart. This is fission, and those are my two new elements, and I give off two neutrons. Okay, this is the splitting of a heavy nucleus into a lighter nuclei. Fusion is just what it sounds like. Put two things together and make a bigger thing. So here's two deuteriums slamming together to make, looks like helium-3. It's going pretty fast. This is the combining of nuclei to form a bigger, heavier nucleus. Alpha particle is the first of the emissions. This is a positively charged particle consisting of two protons and two neutrons. Basically, it's the helium nucleus. And then look what's next, helium nucleus. So it's the nucleus of the helium atom. Here is the helium nucleus, two protons, two neutrons, and that's basically an alpha particle. So if you were taking the quiz, you of course would not pick alpha particle for alpha particle. Okay, beta particle, basically an electron. Okay, it's got that funny B with a tail, and this is the radioactive particle equivalent to an electron. Electron, well, that's a beta particle. Go figure. Positron, this is another kind of emission that we don't get into much, but it had shown up in the past few years more than it had in the past, so I started to include it a little bit more. This is a positively charged electron or beta particle. It's just a beta with a positive. Okay, looking up how these are made, it's kind of neat. Proton, positively charged elementary particle that is fundamental constituent of atomic nuclei. Remember, the number of protons is the atomic number from our previous learning. Neutron, this is another fundamental guy, but doesn't have charge. He has no charge, but has mass, and it's slightly greater than the proton. It's basically the same. Okay. Gamma, now this is the boogeyman. This is that weird little Y. The bottom, this guy is pure energy, no mass. So hence he has the most penetrating power. Neither the atomic number or the mass is changed in the original because it doesn't have any mass or charge to it. It's just pure energy. So in order to protect ourselves from gamma emissions, we need like something like 10 feet of concrete or 6 feet of lead. Okay. Half-life. This is one of the keys to the whole unit. Half-life is the time it takes for half of the atoms in a current sample to decay. Okay. If I have 50 grams, I will have 25 grams at the half-life. Okay. Radioactive decay is the process by which the nucleus of an unstable atom loses its energy. Could be alpha, beta, gamma, or positrons, and they have characteristic, that's the wrong word, it's kind of predetermined which element that isotope is going to give off which kind of decay, and we have a reference table for that. And with that, we're done with vocab. Let's get right into video 3 and get to the nuts and bolts of this.